Hello, welcome to another example with calibration. So in the advanced calibration lecture, I gave a really squirrely example where what if we wanted to calibrate a function from data, if we wanted to choose calibration coefficients that looked like this. So this is pretty bizarre, and what I showed you is that if you just try to use this function as it is, the method we've been using, which is called the method of least squares, it doesn't work because this coefficient is buried inside of a function. It's inside of this exponent. The coefficients have to be out front. Only linear combinations of functions are allowed. It just doesn't work. But I also showed you that, well, but in this one case, we can use a trick by taking the natural log of everything. And so today, what I'll do is I'll actually work through that trick and I'll show you how to do it. Why does this matter? Well, as we already know, now this is less relevant for calibration, but as we already know, there are tons of examples where this function just shows up naturally in nature. Exponential decay of anything, for example. So you saw it with temperature sensors, right? So we see this function show up, and every now and then it's nice to be able to empirically extract. So the method you used in your lab was you captured a scope trace and you calculated the time constant. Right. By the way, this also does show up explicitly in some functions, calibration functions for sensors. For example, the type K thermocouple calibration, the relationship between temperature and millivolt output of a thermocouple, it actually has this term in it. It has other terms as well, but this is one of many terms that's used in the standard accepted calibration function for that sensor. Okay. So, if we want to do this, the trick that we talked about is you start with a natural log. So, I'm going to just take the natural log of everything. And fortunately, because we know our algebraic rules for natural logs, we can just do that. That's easy enough. And now I want to simplify things a little further because now one of my calibration coefficients is inside of a natural log, which we just said is awful for me. I don't want to deal with that. Well, but this whole term is just a constant. What if I just call this a new calibration coefficient? Capital A naught. What if I just say let this whole thing be a new coefficient? If that's true, then I'm good to go. Notice that I'm not worried about y being in a weird function. I'm not worried about my raw data needing to be cranked through bizarre functions. That's fine. I can do that easily. It's my coefficients I'm worried about. I need easy access to my coefficients because that's what I'm solving for today. All right, so we've got a calibration function, and now we need to define an error function. Now, if I define it based on differences in y, I'm going to be in trouble. I can do it, however. I'm going to choose to define my error function now based on changes in natural log of y. So for example, I would do this. And this will work. What if I define my error this way? So, lovely. Then my error squared expected value is this. There we go. Or if I just substitute in for my function here, not bad. All right, now it's time to differentiate. So remember, so I've defined a metric. Now keep in mind, this is just a number, right? You can calculate it for a data set. It's a number that tells you how well you're doing at matching your data. Now, if I play around with these coefficients and recalculate the error squared, right? I can do that at will. We want to find the values of A0 and A1 that minimize my total error, right? So when that's true, at the minimum, the error will become insensitive to little tiny changes in these coefficients, which is why the partial derivative, that is if I hold everything else constant and only value one of these coefficients, that partial derivative will wind up being equal to 0, right? We do this in the same way we've always done it. It's a little weirder now because there are natural logs floating around, but there's no reason to be afraid of that. There's no reason to be intimidated by natural logs because, after all, we do have calculators. All right, now, so I've dispensed with the 2, right? And I don't touch the stuff inside the parentheses, but now I need to multiply by the inside derivative. Because we're treating everything that isn't A0 as if it were a constant, right? The derivative inside of here is easy. It's just -1. That's the derivative of this term, yep, with respect to A0. And that's all divided by n. Well, just like before, we can blow away the 2 because we can divide 0 by 2 and it is still 0. So now I'm free to distribute my summation. Oh, excuse me, forgot to distribute my -1. There we go. There we go. And so finally we have an expression for, we can turn this back into expected values, and we've got ourselves a nice tidy expression. Let's see. Yeah, so that equation should be respected when choosing values for A0 and A1. We still need one more equation. We obtain this equation by differentiating with respect to A0. Now let's do the same with respect to A1. I'll let you do that process. You might have detected by now that there are patterns. So with the first, when I differentiated with respect to A0, I'm just going to rewrite the result I just got. If I repeat that process, this is what I got differentiating for A0. If I repeat that process by differentiating for A1, here's the result I'm going to get. I can do that in my head, not because I'm a wizard, but because I'm noticing the pattern that arises. If you really want to check yourself, obviously go through the work, but this is what you're going to get. All right, so a number of you are probably wondering at this point, so am I going to need to do this on a quiz? The answer is, well, it's not a bad idea. Asking you to derive from scratch these equations right here are great. That's a great extra credit question. On the other hand, usually people don't perform that well on this question on a quiz, so that's an extra credit question. Now, what I will do, though, will do, is give you a set of equations that look like this and expect that you know how to evaluate them and expect that you can solve for the coefficients like we're about to do. So I might give you this and a data set and say, go. All right, so for example, I could then give you a data set that said, all right, here are data points for x and y. We're going to choose really clean data because no matter what we do, it's about to get messier. Now, if I have chosen my coefficients correctly, we should get some shockingly round numbers. I mean, surprisingly round numbers, even inside of all these natural logs and nonsense. All right. So I could give you a data set and say, all right, go. Solve for what, figure out what columns you need to evaluate and solve for them. Well, clearly we're going to need to evaluate expected value x. We've already got that column. Expected value x squared. All right, we're going to need that. We're going to need to be able to evaluate the natural log of y. And we're going to need to be able to evaluate x times the natural log of y. There. All right, so let's go ahead and start solving. So I'm going to choose, why not do this a different way? So you can solve for a0 and substitute in and then solve for a1. Or we could just do row reduction. So if I multiply this whole thing by negative expected value x, and then I add the two, here's what I get. So you get the same answer if you do substitution. It's just a little longer. You get exactly the same answer. All right, so there we go. I can also solve for capital A naught. You got to do that anyway, right? The easiest way to solve for this is by extracting it from the first equation. So once we found A1, we can back substitute. This should feel a little familiar. This should feel a lot like solving for B. In fact, it's just like solving for the offset B in mx plus b, right? In the linear equation. It's really similar. Okay, so this is something you might have to do yourself. Not might, will have to do yourself on a quiz, right? Solve for these coefficients. All right, so let's evaluate these columns. So we're ready to start substituting into here, so we need these columns now. All right, well, so we only have 3 data points, not too bad. That's just to reduce the tedium on this. So here, the expected value is obviously 1, so 0 plus 1 plus 2 is 3, divided by 3 is 1. 4 plus 2 plus 1 is 7, divided by 3 is 2 and a third. Just 2 and a third. I'm going to use fractions for a minute. We don't actually need this value anyway. Expected value y doesn't appear anywhere here. Okay, x squared, 0, 1, 4. All right, so here we've got 5 thirds. Let's leave it as an improper fraction. As it turns out, that's going to be easier. But that would be the same thing as 1 and 2 thirds. All right, the natural log of y. Now, I'm not going to try to do that in my head. Let's go to Python. There we go. Oops. Let me import my math library, and I'm good to go. So I'm going to take I need to take a log of 4, and I need to take a log of 2, and I know the log of 1 is 0. So here's what I get. 1.38. I'm going to carry a lot of sig figs just to make sure I don't accidentally round away some nice number. So 1.38629. And the natural log of 1 was 0.693147. Lots of sig figs. And the natural log of 1 is, and always will be, 0. Okay. Here we go. The x times the natural log of y. Well, here x is 0. Natural log of y, it doesn't really matter. It's 0. 1. Oh my, that's nice and simple. 0.693147. then 2 times, 0 is 0. All right, the expected values turn out to be a lot easier than they look. This, as it turns out, is the natural log of 4 is the same thing as the natural log of 2 squared. So in other words, this is double this one. So the average, when I add these together and divide by 3, I just get this again. If you don't believe me, try it in your calculator. Here, when I add these together, right, I just get this. That's easy. When I divide it by 3, fortunately, well, there's a lot of there's a lot of nice symmetry here. So 6 divided by 3 is 3, or excuse me, look at me, I'm screwing up. So 0.231, and I guess that, yeah, that wants to be 0, well, 4, and then that's going to be 4, 5, I think. Yeah. Okay. No, excuse me. That shouldn't be 5. Let's see. Well, all right, fine. I'll use my calculator. Two, 3, 1, 0, 4, 9. Yeah, there we go. The last digit was 9. I should have been able to come up with that. All right. Doop. Back to this. All right, so we've got our entire table, and we've got a derived solution for for our coefficients. Time to plug in and solve. So, in we plug. A1, which was, remember, this is the coefficient inside the exponent. So this is like the lambda in a time response. So A1 is, what did we say? Let's refresh our memories. Expected value x times natural log y. All right, that's here. Minus expected value x, which is, last I checked, 1, times the expected value of the log of y, which is 0.693147, divided by expected value x squared, which we said was 5/3. Well, okay, I guess I can just write that out since I'm using decimals everywhere else. Minus expected value x squared. So that's just 1 squared. All right. 5/3 minus 1 is, that's just 2/3 in the denominator. I'm going to use that in a minute. Okay. Click. So, to evaluate my numerator, 0.231049 minus 0.693147. Oh dear, it's negative. Is that okay? Yes, it's okay. Of course it's negative. My numbers are decreasing. My numbers for y are decreasing, so yeah, there's a negative slope. All right, we're going to multiply that by 3 and divide it by 2. And we've got, it seems to have simplified a bit. I wonder if that, why that number even looks kind of familiar. I think I've seen that before somewhere. I wonder what it's going to turn out to be. All right, that's negative 0.693147. Strangely enough, you might recognize that as negative of the negative of the natural log of 2. I wonder why. Okay, come back to the camera. Here we go. Now we're ready to solve for capital A naught. A naught is, again, just our, of course you can't see that, sorry. Natural log of y minus this thing we just calculated. Let's write that out. amazing. Times expected value x, which was just, oh dear, 1. Fortunately, all right, and so A naught is this. All right, so what does all this mean? What we solve for are the coefficients in this equation. If we want to go back to this equation, excuse me, A naught, we need to substitute, oh, excuse me, not natural log. Right? That relationship. We need to substitute that relationship. Notice I get that. If I just raise this whole thing to the e power, you actually get this expression on the right-hand side. I'll let you prove that to yourselves. After all, it's only algebra. You can do that. Okay, so let's figure that out. So A1 we've got already. That's this number, whatever it means, why ever it's that number. We'll figure that out in a moment. But this number is going to turn into something very simple indeed. So let's find out what. So the exponent of 1.38629. Well, look at there. To the number of sig figs that I worked the problem, which is obscene, that is exactly 4. So we get that y is equal to 4 times e to the negative 0.693147. Times x. Wow, that came out evenly. Now I wonder why this is what it is. Well, as I observed before, notice that this is the same thing as the natural log of 2. We happen to have calculated that already. Look, it's right here. It's the natural log of 2. So that's interesting. I'm just going to do a little bit of algebra. Yep. So after I use a little bit of algebra, I find that this is what my optimization gives me. So, I mean, you'd have been fine to express it this way. This is also correct. I just did a little bit of extra work to show that it's actually a really even number. Why is it so even? Well, basically what this means, this is a geometric series, is every time you can think of it as an exponential decay, or you can think of it as a geometric series. They're equivalent. The algebra I just did shows you that. For every increment in x, I halved y, right? Y went from 4 to 2 to 1. Well, that is exactly what this geometric series tells you, and it's consistent with the exponential decay we just evaluated. Neat. So there's yet another example of this error analysis, this calibration analysis, doing its thing and giving us useful results. All right, thanks for watching.